Hi everyone, I am Dr. Ajay Yadav, course coordinator of this course Introduction to Electrical and Electronics Engineering. Along with me, Dr. Umesh Sharma is also part of the team. So in this course, if you see, these are the textbooks and reference books. These are available in the library. You can refer there. In addition to, we have reference books also. In the syllabus, if you see here, the basic module 1 is uh, it consists of basic circuit theory, concepts like charge, current, voltage, Ohm's law, Kirchhoff voltage law, Kirchhoff current law, some examples of periodic signals, how to calculate their average and RMS value. If you have resistances in series and parallel, how to calculate the equivalent value. This is followed by voltage and current division too. And if you have some complex circuits, then how you solve by the help of nodal and mesh analysis. This is followed by network theorems, where we solve the uh, uh, complex circuits by the help of maximum power transfer theorem, source transformation, superposition, and Thevenin and Norton theorem. All these theorems are there so that we can simplify our circuits. In addition to that, in module 1 we have some basic concept related to capacitor, phasor diagram, a series and parallel combination of capacitor. Similarly, same thing for the inductor, how to calculate the equivalent inductance when you have inductors in series and parallel, impedance and frequency dependency, what are the units of these inductor and capacitor. Uh, After that, application of resistor, inductor, and capacitor in the form of low pass, high pass, and band pass filter. This is followed by a brief introduction of application of these concepts. A good example is your mobile phone charging circuit, car headlight, and electrical systems. In module 2, we will cover the basics of diodes, where we start with the semiconductor materials. What is a semiconductor material? Uh, Intrinsic, extrinsic semiconductor material, how to dope them. Uh, uh, in addition to that, we have diode circuits, where we start with basic p-n junction diode, how p-n junction is formed, uh, the application of p-n junction diode in the form of half wave and full wave rectifier, and how to calculate the efficiency of the rectifier circuits, the ripple factor. All these things are will be studied. In addition to that, we have Zener diode and its applications, and the concept of transistor in the form of BJT and MOSFET will be explained to you. It has its transistors, they have their own applications in the form of whatever processor we are using, because there are chips there in the form of processors in your laptop and computer, and there are automatic street light systems. There we use some sensor circuits. So all these are applications of your transistors. In module 3, we will cover basics of op-amp. Uh, it starts with the characteristics of an op-amp, then application of op-amp in the form of inverting, non-inverting amplifier, integrated differentiator, and different sensors in the form of temperature sensor, light dependent resistor, ultrasonic sensor, and actuators like LED, servo motor, and DC motor. They will be discussed. These are the experiments which are part of the uh, syllabus. So I'm starting with module 1. If you see in module 1, it is about basic electrical circuits uh, concepts. But here I'm starting with history of electronics, because you should know why we study electronics, especially for computer science students. So yeah, I go back to 1904 when John Fleming invented the simplest vacuum tube, that is a simple diode. And here, if you see in this diode, you have a anode and you have a cathode. So cathode is emitting electrons, anode is collecting these electrons, and this is the physical structure of the simple vacuum tube, which consists of the glass structure from the outside. Inside this you have a vacuum, but the drawback of this vacuum tube was that it was consuming a lot of power. At the same time, in around 1946, you will find that the first means giant computer, that was called electronic numerical integrator uh, and computer. It was used in the University of Pennsylvania, where if you see in this computer, it was 1000 times faster than electromechanical computer. It was hangs around 17,000 vacuum tubes, 7200 crystal diodes, 1500 relays, 70,000 resistors, 10,000 capacitors, 6,000 manual switches, and around 5 lakh hand soldered joints in this computer. So you can imagine how big it was, and it was consuming a lot of power. It was consuming around 150 kilowatt of power, and we were giving input from punch cards from IBM. It was having the clock frequency of around 100 kilohertz. Uh, at that time, when people were working with them, you can see that the person he himself is seeing what is happening where. So there were several tubes burnt out almost every day, and so half of the time you can say that it was not functional. Now, if you see in this case, this ENIAC computer, it could perform complex sequences of operations like loops, branches, and subroutines. When the first of all, we will figure out the computer on the paper, program on the paper, and then it took days for loading the program into the ENIAC using switches and cables. So this was the at that time. If you see the task of implementing a program based problems and mapping into an act took few weeks. Okay, and the programmers they debugged problems by crawling inside the massive structures to find bad joints and bad tape or bad tubes. So if you see there is an error in the program or any thing is there, so they have to crawl inside this massive structure. And the first test problem was computations for a hydrogen bomb. So this was the first test problem for this computer. Now, when we talk about computer, then as I told you, we use these are basically uh, designed and developed by the help of transistors. And so after the vacuum tube, which is a diode, then we had transistors. Vacuum tube, as I told you earlier, it was very power hungry and fragile because of glass structure. So in 1947, Shockley, Burdin and Britton at Bell Labs, they invented the first transistor, and it was a point contact transistor. The first transistor was a, if you see here, it consists of a emitter, collector, and here in the outer side there is a gold coating, and this at the base you have it is corrected here in the point. So that's why we use the term point contact transistors. Thus, generally we studied junction based transistors, if you see in this course also. So this is how, this is the first transistor which was invented by the scientist in at Bell Labs, and this is the physically also you can see it how it looks. So it was, if you see here, the first transistor which was invented by Shockley, Burdin, Britton at Bell Labs. Now these transistors, they have, like, we can classify them into bipolar junction transistor and metal oxide semiconductor field effect transistors. So in from 1950s to 1970s, before most technology became dominant, so we were using BJT in early computers, and they were having high speed analog amplification and switching. Okay, this was the property of the BJT which is used, and it has applications like voltage regulators, clock drivers, power management circuits, RF and analog interface circuits. All these circuits are based on them. This is followed by we use this MOSFET as the building block of modern digital ICs. We have CMOS technology which use NMOS and PMOS, and in terms of power consumption, they were using very low static power. They were having high switching speed and high integration density. Okay, so it is used in CPUs and GPUs. Microsoft microcontrollers and silicon chips, so they also use them MOSFET. Then in the memory, also we use them FPG and ASIC chips, digital signal processor, AI accelerators and neural processing units. So if you see, we use transistors a lot. So the basic question ki why we study diodes, transistors, I think it's clear because all these microcontrollers, memory, your processors, they are all using transistors in them. Okay, transistors, diodes as part of them. Okay, so that's why we teach them. We teach this. Now I'm starting with basic electrical parameters, and the first parameter is your charge. If you see, charge is an electrical property of atomic particles that governs how the particles are affected when you apply some magnetic or electronic field. We measure the charge in coulombs. There is one very famous law of conservation of charge which states that the charge can neither be created nor destroyed, it can only transfer. Okay, and the algebraic sum of electric charges in a system does not change. If you see, the magnitude of the charge is around 1.6 into 10 per minus 19 coulomb. This is electronic charge. So we are using negative sign here. Similarly, there is another property that is called, or another parameter, that is your current. Current is what time rate of change of charge, and it is measured in ampere, and 1 ampere is 1 coulomb per second. So mathematically you can define that I is what? It is dq by dt. If the current doesn't change with time but remains constant, we call it a DC current. And if it is varying with sinusoidally with time, then we see AC current. So if in terms of representation, if I say that this is your AC and this is your DC current, okay, this is with respect to time, it is varying with respect to time. So these are the two type of currents. Then there is another property that is called electric field, which is force, electric force per unit charge. The direction of the field, if you see, generally the electric field is radially outward from a positive charge and radially inward, or it is towards the negative point charge. Based on the there is another property that is called voltage of potential difference. So it is the amount of work done in moving a charge from one point to another point. We measure the potential difference or voltage in volts. So V is given by dW by dq. Okay, and similarly we have another property that is called resistance. So resistance is what? It is the ability to resist the flow of electric current. It is measured in ohms, and if you have a electrical wire, then you can measure the resistance of that by the help of this formula, where L is the length of the wire, A is the area of projection of the wire, and rho is the resistivity of the this material from which this wire is made up of. So you can say that, suppose that if it is copper wire, then resistivity is different. If it is aluminium wire, then resistivity is different. So corresponding resistance value will be different. Okay. Now this is I have given you a example where, suppose that if I connect a battery source of around 5 volt here. Okay, this is around 5 volt here. So current will flow from positive to negative in this direction. If I opposite the polarity of the battery which is connected, means negative will come here and positive will be here. Then this is negative, this is positive. So opposite direction, current would flow in the opposite direction. We will say that your VAB is minus 5 volt here and it is plus 5 volt here. There is another important concept, that is your ground in electrical and electronic circuits. So this is around 0 volt. So you have, these are the two symbols. You can show ground by the help of this also and by the help of this also. So both is denoting your, these are your ground voltage. Okay, so generally it is 0 volt. Now if I talk about the periodic signals, then uh, periodic signals are, as it indicates, by the help of a function f of t, which is ft is what? T plus nt, where n is an integer and t is the time and capital T is the time period. So if we can consider this by an example. Suppose that if you have a sinusoidal voltage Vt is equal to Vm sin omega t, where Vm is the amplitude of the sinusoid, omega is the angular frequency in radian per second, and omega t is the argument of the sinusoid. So the sinusoid repeats itself every t seconds. If you see here, after every t second the sinusoid is repeating, and thus t is called period of the sinusoid. Okay, where omega t is equal to what? 2 pi, or t is equal to what? 2 pi by omega. So this Vt plus t, you can say that for any periodic signal this is applicable, that Vt plus capital T is equal to the function V of t itself. The period t of the function, periodic function is the time of one complete cycle or number of cycles per cycle. The reciprocal of this quantity is the number of cycles per cycle, known as cyclic frequency of the sinusoid. And if you see here, this is a waveform where the path traversed by a quantity uh, as a function of some variable is your waveform. So generally in the periodic signals, here we use the time as on the x-axis and voltage on the y-axis. Instead of voltage, you can use current. It's okay. So for a waveform, it will be like this. What is instantaneous value? It is the magnitude at any instant of time. The magnitude of this waveform at any instant of time is your instantaneous value. So generally suppose that at t is equal to small t, means t1, here voltage is small, this b1. Okay, so this is your instantaneous value of this signal. Peak amplitude is what? It is the maximum value of waveform as measured from its average or mean value. So this is a pure sinusoid wave. So its average value is what? 0. So from this 0 reference, what is the peak value? That is your this V naught is your peak amplitude here. So this is your peak value of this waveform. Okay. So then we have another concept that is called peak to peak value. So if this is plus V naught, then this will be what? Minus V naught. So peak to peak value will be what? V peak to peak. It will be what? V naught minus of V naught. So it will be what? Twice of V naught. If V naught is 5 volt, so peak to peak value will be what? 2 into 5, 10 volt. So this will be 10 volt. Okay. So you can calculate peak to peak. For a periodic waveform, it repeats after every capital T time interval, and the waveform is shown here. It is a periodic wave. Here capital T denotes the period, which is the time required for completing one cycle, and F is your we can say that frequency, or we also use the word cycle here. The portion of the waveform that contained in one time period is your one cycle. So this is one cycle. Okay, this is one cycle. Up to this, from here to here, this is your one cycle. Now there is another it's very famous. Uh, we calculate the average or value of the signal by the help of this formula. So if you see here, average value is defined as the average of all instantaneous values of a wave over an interval. So average, generally we consider average over one complete cycle in electronics. So here the average is estimated by finding the area under this f of t curve. So ft is a wave equation. So the area over two time instants, that is t1 to 2, is your area. And if you want to calculate average of this, so you will divide this by the time interval. Okay, so this is how, this is your average value of this signal. If you want to calculate RMS value, then it is defined as square root of mean of squares of the instantaneous values. So first of all, you have a function, you will take square of that, then you integrate over the interval t1 to t2, and then divide by this time difference between two instants. This is your uh, average of this square. Then we take the square root. This is how we calculate the RMS value of a signal. Now there is another concept that is called phase difference. In the phase difference, we calculate, we check if you have two waveforms, what is the phase difference between them. Suppose that if you have a reference signal FRT, which is AM sin omega t, where AM is the amplitude of the signal and omega is the gradient frequency and t is the time. So, and you have another signal, that is f of t, which is AM sin omega t plus theta. You can calculate, or you can say from here that because if you see here, f of FRT at t equal to 0, FRT is what? 0, but ft is having some value. So you can say that ft leads FRT by an angle theta, or you can also say that ft and FRT, they are out of phase by an angle theta. Okay, so this is the concept of phase difference. Similarly, you can say that if I reverse the situation, here you have a signal ft at t equal to 0, this is equal to 0, but FRT it is having some value. So your f of t is what? Am sin omega t minus theta. So in general you can say that FRT leads the FT by angle theta, or they are out of phase by angle theta, or you can say that FT uh, lags FRT by an angle theta. So this is the concept of phase difference, which you can see by the help of seeing the waveform. You can check whether they are leading or lagging the another waveform. Okay, so that's it for today. So I am stopping here. Thank you.